all we're doing in topic 9 is we are simply combining atoms together. But this time we're going to combine metals and non-metals. Back in topic 8, you actually were combining atoms, but you were combining a bunch of non-metals which were forming covalent bonds between them, and you were trying to get your octet to do it. In topic 9, hey, we're still combining atoms, but now we're going to combine these two, which forces us to form ionic bonds, which now means those oxidation numbers add up to 0. That's the key. And that's our favorite number now. Now, we're taking shortcuts. I'm not going to make you go back to topic 5 and use that electron configuration, go find a valence, go figure out if it's going to gain or lose. We're taking the massive shortcut. We have to, otherwise this class would last for 5 years. You should now know that we can obtain oxidation numbers simply by using this table and using the numbers in these spots. The only tricky thing is, man, you better have a table where you can tell the difference between a bold number and a normal printed number. So hopefully, and I think you can, because I think you told me last week that you could see the bolds. So that's going to be the key. All right, so for part 1, we are going to pick the bolds. We are going to get these oxidation numbers to equal 0. Let me just get an example up here so we can see all this. So, example problems. Okay, here we go. So, we'll take vanadium and we'll add it to selenium. Alright, here's the routine that I have. I'm going to take these two guys and I'm going to combine them. I'm going to put them side by side. Now I need some oxidation numbers, so now it's time to cheat off the table. Vanadium, there he is right there. And I can tell on my table that he has a +5. That's his most stable oxidation number. Now, selenium, you have to remember that the front guy will always be positive because he will be the metal. And the second one is going to be negative. He's going to gain electrons because he's going to be the non-metal, or he could be a metalloid. But you already know that it has to be a negative number. So every single time, the positive guy will be in the front, negative guy will be in the back. So now I know he has to be negative. You got to find selenium. And there he is. And no, you cannot pick that bold 4. You have to pick his negative option. He's trying to gain electrons to obtain the octet. Because he has a valence of 6, he's going to gain 2. So you have to grab that -2. Now the goal is to get these guys to add up to 0, because right now you are in trouble. That is not going to work. And this is where I mentioned to you last week, we can do a system that's called drop and cross. Massive, easy shortcut. Drop and cross, it's like it sounds. You drop the 2 signs and you cross those numbers. So I'm going to do this. I'm going to drop that sign. I'm going to bring that 5 over here. I'm going to drop that sign. I'm going to bring that 2 over here. And sure enough, if I go back and look at this, 2 times a -5 is -10. And then 5 times a -2 is a, whoops. Oh, I just caught that. It's a +10. And then 5 times a -2 is a -10. And there you add those guys up. And that is your 0. Drop and cross. You will drop and cross forever now. It's so quick and easy to get that 0 to show up. All right, let's do this. Find your table. Let me give you a couple practice problems, and then let's throw in some of these guys as well. Remember, these guys will always occupy this second spot because they have negative oxidation numbers. Okay. Let's get a series of problems here. How about you deal with manganese plus phosphorus 3, samarium plus sulfur. Before you start number 3 or number 2, I'm going to show you where, man, you got to get the right symbol. Samarium on number 3. I'm going to show you where that sucker's at, otherwise you're going to spend 20 minutes locating him. He's down here at the bottom. He's right here. So be prepared. Some of these guys in this period will show up once in a while. I know it's kind of hard to search this table, 118 elements, and you're looking for just one. Yeah, it might take you a while. So I'm going to warn you, that sucker is sitting down here at the bottom. The majority of them will come from your transitional metals that we've talked about in topic 6. Okay, man, put them together, get their oxidation numbers. Use the bolt numbers for the guy in the front. Drop and cross. All right, go. All right, let's see what you got. Manganese. Isn't he a +2? Yeah, he's a +2. Phosphorus sitting way over there. Don't forget, man. You cannot grab that 5. You have to grab its only negative number. Now remember what that plus and minus means. That plus or minus 3, what is it, 357? 354. That 354, what that really means is -3 plus 3 plus 5 and plus 4. So that plus or minus, just that number in front, everything else behind it is going to be positive. They do go in order. So the most abundant or most common form would be this, obviously. But then he can do this little trick, and then this, and then this. Your main thing is to use the plus minus for the second atom every time and use only the first number. Okay? So I don't have a choice. His only negative option is a -3. You drop those signs and cross those numbers, your answer can only be that. Samarium, you know, I think the crease of my table is right, it's right, I can't even see that number. I think it's a 4. Or a 3. Probably a 3. Can you see it on your table? Is that a 3? I think it's a 3. 3, and then sulfur sitting over here, plus or minus. You don't have a choice. You have to use the negative option, which for him is a -2. I'm going to simply drop and cross. I'll bring that 2 over here. Bring that 3 over there, and you are done. Now, you do have to erase these numbers. So if you wanted to see what it should look like as a final answer on your assessment that's due next Monday, you have to go back and you have to get rid of these things. And that is what it should look like. There's your final answer. Okay. Let's now bring in these good old polyatomic ions. Okay, so let me get rid of this. Don't change how you do these, except now when you drop and cross, you might have to add some parentheses to these guys. So number 4 let's go Fe. Sorry, I don't want to use two of them. Let's go iron, because I want Te here. 5. How about some palladium and some chlorate? 6. Some bismuth. I don't want to use him again. Oh, yeah. Let's use Si03. Let's use some silicate. And 7. How about some silver phosphate? Alright, so don't change how you do these things. The guy in the front is always going to be the positive metal, going to lose electrons. These guys require electrons to become stable and form those octets. So you are simply going to place them, you're going to place them side by side. SiO3 and good old silver phosphate. Okay, you don't have a choice. Negative, 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 negative. Positive, 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 and positive. I'll do number 4. First step, look up this guy in front, look up that metal, find his most common state, and for iron, oh, my camera never likes it when I don't have both sides open. Boom, you have to pick, I'm going to get that shade just right, you have to pick that bold 3. Now come these package deals. If you ever see a bunch of capital letters, meaning multiple atoms, get your eyes on the polyatomic ion sheet and you have to search TeO4. Oh, good heavens. There he is. Got him. Tellurate is his name. And right there's his oxidation number. And of course, that's considered bad because they don't add up to 0. So be prepared for me to say that the rest of the year. I'll ask you, hey, is this good or bad? And it's bad if they don't add up to 0. If they do add up to 0, that would be good, and you would simply do nothing. You do not drop in cross, nothing, because they've already equal 0 when added together. That's bad. Those two do not add up to 0. So I will drop the signs and cross those numbers. So this 2 is heading over here. This 3 is heading over here. But when you need 2 or more, any of these off of that polyatomic ion sheet, you must use parentheses. Because if you don't, it looks like you want 43 oxygens. So when you drop that over, and this sucker is on that polyatomic ion sheet, your favorite symbol comes back into play. Good old parentheses. And then you go back and you erase these, obviously, and you're done. Okay, man. 5, 6, 7. Let's pound those out. Let's see what you get. Okay, good old palladium. I always forget, I think he's a +2 palladium. Where'd that sucker go? Yes, he is a +2. +2 chlorate. That thing is a -1 off of your table. Dropping and crossing that, I'm going to do this. I'm going to bring these and that. And then I have to go back and say bye-bye. Cha-ching. Bismuth. Where in the heck is bismuth? He's a huge, oh yeah, he's huge. All right, +3. Silicate off of your polyatomic ion sheet at -2. I'm going to drop and cross that. Put a 2 there. Bring my 3 over here, but you need to add some parentheses. Silver, I think he's a +1, I think. Yes, he is. +1. Phosphate, -3. And drop and cross that would be just that. Don't wrap him in parentheses. You do not need to do this. That's a no-no, because it's a single atom off of the table of silver. No parentheses, just these guys receive the parentheses. If you need 2 or more, because this one comes over here and really does nothing. All right. And then obviously, yes, I know, get rid of these. Later on, we'll have to keep them. But for now, erase those suckers. Okay, that's part 1. Now the part 2. The part 2 is they're going to give you the formula, and they want you to calculate these oxidation numbers at the top. So it's a complete flip. They're going to underline the part of the atom they want you to calculate. We also have a second question that goes along with these, and that is the total number of atoms that are inside these compounds. It's a complete setup for a later topic. So I would definitely work on that now, so later on, it's not like, what am I doing here again? These problems look like this. So I would say, hey, here's part 2, and it is completely flipped. So now you get RE, and they'll underline it, and then they'll give you the second part of the compound, and now they're going to ask you 2 questions. Obviously, they want to know the oxidation number, and now total atoms. This is the key. This one is a complete setup for a later topic. This one is actually a very huge part of your next topic. Topic number 10. Huge part. All right, so what do? Never look up the one that is underlined. Never look them up, because some of these have multiple bold numbers, like I showed you last week. And the best example is ruthenium. He has 2 bold numbers, so it doesn't pay to look up the one that's underlined. Your first reaction should be, okay, yeah, I'll find out what he is. To find out his oxidation number, you have to use his partner. You will look up the partner. Selenium. He's on the non-metal side. He has to be negative, and sure enough, there he is. And his only negative number is a -2. But you have 3 of those in this compound, which means the total is -6. If this side's -6, this side has got to be the opposite, so they add up to 0. So you know that the left side has to be a total of +6. But they want the charge per individual rhenium atom. And so you will always end these problems with some pretty simple division. And the math is pretty easy. +6 divided by 2, your answer is a +3. And that is what they want right here. And that is going to come back into topic 10. This column, students actually like this column. It's really straightforward. Now, it's going to get more complicated, obviously. We didn't get that far last week. But today, you're going to have some pretty large numbers in here. To count the total, all you do is go back and look at the original formula. Looks like I have 3 selenium atoms, and it looks like I have 2 rhenium atoms for a grand total of 5. This only gets complicated when parentheses are used when these guys show up, which we'll definitely take a look at here. Okay. There's the steps. So I'm going to keep these steps here. I'm going to put number 2 down here. Number 2, let's do this one. I'm going to do 6 iodines, 2 osmiums. Okay, I want to find this one. I want to find osmium's oxidation number when 2 of them are combined with 6 iodines. And the 2 questions are the same. All right, go ahead and do that one. And then we're going to bring in these lovely polyatomic ions and see how that changes us up a little bit. Take a look. All right, underline guy, don't waste your time. You will have to look up his partner, and he is a -1, but I do see that there's 6 of them for -6. If the right side's -6, left side's got to be the opposite, and then I'll divide by how many osmiums are in the formula, which is 2, and yes, it's the same stupid answer as the first one. Oh well, hey, man, you never know. +3. Total number of atoms, I like doing these. Hey, you got 6 iodines in here. You've got 2 osmiums for a grand total of 8. All right, it's time. Let's bring these bad boys in because we're going to be using these the rest of the semester. Let's grab some of these and throw them in the mix. Okay, let's see. Rules still apply, so whatever is underlined, don't waste your time looking them up. So let me get rid of this. Get rid of this. Not anymore. Okay. Let's throw in some of those polyatomic ions. Number 3. All right, let's grab some. No. You're not ready for that one yet. Let's do this. Let's calculate his charge when he is combined with 2 off of the gold sheet. Okay, I'll do this one. I'll show you how this one works, and then I'll let you try some on your own. Okay, the rule is still the same. I don't care if this part's underlined, don't look them up. So MO, all right, well, who cares? All right, I need this guy. SO4, here's your combo deal. You got 2 capital letters, so it's going to be on here somewhere. And if you search, there he is. He's at -2. But I see that in the problem, I've got parentheses, I've got multiple of these guys. I've got 2 of them for -4. If the right side's -4, the left side has got to be the opposite at +4. But I need to divide by the total number of MOs that are in this formula. And there is a 1 there. They just only have to write it. And 4 divided by 1, you gotta love this kind of math. Easy. Easy. Okay, here you go. Total number of atoms. We did this way back in topic 3, where we had parentheses and we were distributing the number on the outside and multiplying by the stuff inside's atomic mass number, the A number. Well, we're not using the atomic mass number, but we are going to distribute. So what I have to do now is play the game carefully. All right, so I'm going to distribute this too. 2 times 4 gives me 8 of those. And then 2 times 1 sulfur gives me 2 sulfurs. The MO, not part of the parentheses, he's outside of the parentheses, which means this 2 does not pertain to him. He's just all by himself. I don't see a number there, which means there's 1 actually there. And then add those things up, and you get 11. Not a big change, just be very careful with the number on the outside and distribute him in carefully to each and every one. Okay, let's now, now I have to show you this one. Well, not show you, I'm going to have you try this one. Let's use good old rhodium and a C2H6O2. But now, this part is underlined. Remember, don't change how you do these. It doesn't matter which part's underlined. The process is still going to be the same. And let's get in the 2 questions. All right, give it a shot. Rhodium, I'll save you some time, is sitting right here in the middle of the table. All right, okay. First step, don't even look him up, because you probably won't find him on that polyatomic ion sheet. These are just the most common ones that we will use. There are some uncommon ones that exist, and this will be one of them. So, again, don't look them up. Okay, yeah, you better look up rhodium, and he is a +3. I do see there's only 1 sitting there. Okay, so if my left side is +3, this side has got to be the opposite at -3. And here's where it gets a little tricky. You have to look carefully and see how many C2H6O2s are actually there inside this formula. And there's only 1 of them. You can't say there's 2, because if there was 2 or more of these, there would have to be some parentheses in here. And then the number on the outside, whatever that might be, then that's the one that you would divide it by. But if I don't see parentheses, there's only 1 of those in there, and that is commonly missed by students doing this the first time. Have to be very careful of those guys. The total, oh, this isn't too bad. I don't see parentheses, so this isn't too bad. Looks like we've got 2 oxygens, we've got 6 hydrogens, we've got 2 carbons, and we have 1 rhodium for a grand total of, how did I do that? I got lucky on that. And how I got 11. Okay, I'm going to give you one more of these ones in the back that are underlined. Those are the commonly missed problems every time I teach this. These are the ones that cause problems, because the number here is usually wrong, and here when there's parentheses. So I'm going to erase this mess. All right, here's number 5. Still the same 2 questions. All right, number 5. Let's see how this works. SR, let's go 2, let's go C4H9O3, underlined, and a 2 sitting right there. All right, be careful. Give me his oxidation number and the total number of atoms. All right, let's double check. Let's see. Oh, underline guy, who cares? I don't care one bit. Strontium, +2. He only has 1 possible number, +2. There it is. But I do see there's 4 of them. Oh, sorry, there's 2 of them for a grand total of +4. So if the left side is positive 4, the right side has got to be the opposite at negative 4. But now I see parentheses, so now I know there's at least 2 or more of these things, and that's the number I need to use. Put that down there. And negative 4 divided by 2 is negative 2, and that's what goes there. Yikes, look at this total. Looks like 2 times 3 will give me 6 of those. 2 times 9 gives me 18 of those. And then 2 times 4 gives me 8 of those. And thank goodness there's only 2 strontiums. What the heck is this? 18 plus 6 is what? 24, 32, 34? Whew. Bingo. That's a good one. Man, if you can do that one, you're in good shape.